So this work, at least to me, has been inspired by the literature in the cognitive neuroscience domain. Our mental models, made up of our unique experiences, determines how we interpret the world. They also affect our actions, how we assess opportunities, and also help us solve problems in our everyday lives. In a sense, how we look at the world is through the lens of our mental world models. So in this work, we explore building generative models of game environments. And we also try to train agents to look at their worlds through the lens of their own generative world models. So our generative models consist of pretty basic components. To develop a representation of space, we use a variational autoencoder to compress screenshots of a game into a low-dimensional latent space. To learn a representation of time, we train a recurrent neural network to predict the distribution of future events. Just like how in this network, we train a recurrent neural network to predict future pen strokes of a pen, and we can sample from that distribution to generate different doodles. In our case, rather than modeling pen strokes, we model the distribution of future latent vectors encoded by our VAE, so we can sample trajectories of the future. So in our setup, we have an environment that gives us a pixel image at every time step. We feed this pixel image into a variational autoencoder trained to reconstruct it, and the encoder will output a low-dimensional latent vector Z, our representation of space. We then feed this latent vector Z into a recurrent neural network called M that's trained to predict the distribution of future latent vectors, conditioned or depending on the current information and previous information. And the model M has a hidden state H, and this hidden state of the RNN we're going to use as a representation of time. We'll feed these two low-dimensional representations of Z and H, representing time and space, into a small linear controller C. Now, our controller C can only see Z and H. It cannot see the actual pixel observations. And its job is to output the action A that will affect the environment, causing the environment to generate the actual states for the next time step. And to train our controller C, we want to solve for the parameters of this linear controller such that we maximize the expected cumulative reward of our agent acting in the environment. So to test this simple framework, we tested on a car racing from pixel task from OpenAI Gym, where the agent has to navigate through these randomly generated tracks as fast as possible. So in the procedure, we first collect a data set using dataset rollouts using a random policy. We then train the variational autoencoder V to encode each frame of this dataset into a low-dimensional latent space. So we can then process this dataset into a latent space version of the dataset. We then trained the recurrent neural network M using this dataset to model the distribution of future latent vectors conditioned on the current and previous information. Now, the important thing to note is in this experiment, VMM does not have access to the reward information. Its job is simply to compress space and to predict what's going to happen in the future. So these two networks can actually be trained efficiently using a GPU on a data set in an unsupervised fashion. So while these two models combined have millions of parameters, the controller, in contrast, is a very small model because of the low dimensionality of the inputs, and it has less than 1,000 parameters, which makes this really easy to solve. And in our case, we can even use evolution strategies, in our case CMAES, to solve for the parameters of this linear controller such that we maximize the expected cumulative reward of the agents. And here's the citation of the cake that's correctly done. So here's an example of, on the left side, of the actual input frames we feed into our agent. And on the right side are reconstructions using the decoder of the VAE using the latent space. At the beginning, we also train an agent using only Z, not H. So we only give it the spatial information, but not the temporal information as an input. And it still learned to drive, but the policy, the navigational policy, is very non-robust, and it wobbles a lot, tends to miss the sharp corners. But when we then give it also H, so it knows both Z and H, the spatial and temporal information, it learns a more robust policy to navigate, and it's able to seemingly attack these sharp corners by predicting what's happening in the future intuitively. So our model achieved an average score above 900 for this task required to solve the task. And to our knowledge, this is the first solution that's able to solve car racing V0. But that's not the end of the story. This paper has been out for a few months, and people have taken our code or the framework and did interesting things with it. So someone used this framework, but rather than training M, they randomly set the weights of M, and they showed that by using these random temporal features, the score is still okay. So I found that quite interesting. Maybe it's not the weights, but the architecture that makes everything work. Another team, it doesn't mean that DQN is bad or anything. Another team improved DQN, made it 3-layer network with put in dropout and curriculum learning and all this stuff, and they also achieved a score at 900. But the difference here is that in our case, we use a generative model, and our model can predict future frames. So in theory, we can try to replace the environments with an environment generated by M. And we can try to train our controller not using the actual environment by training the controller entirely inside of an environment generated in latent space. So training inside a latent space environments. So to do that, we can take the output of the RNN-M and feed that into a mixture density network layer, an MDN layer, and so that it outputs the probability distribution function of the next time steps of the latent vector in the next time step. We can then sample a next Z, a realization of what's going to happen next, and feed that back in as if it's the actual latent observation. So we can train this controller inside this generated latent space environment, not using the actual environment and not using any pixel information, and we don't require the VAE. So we test this on a simple VizDoom level, where in this level, the agent's unfortunate agent is stuck in a room full of monsters shooting fireballs at it, and its job is simply to survive as long as possible. So the procedure is largely the same as the car racing task, with a key difference of the RNN-M model. In addition to having to predict the probability distribution of the next latent vector, it also has to model the distribution of whether the agent dies or not, and we can sample from that. We need to model this the termination events, because in order to replace the actual gym environments, to get the done events with the generated environment. We then train a controller inside of this generated latent space environments, and then we can deploy these learned policies back to the actual environment to see how well we transfer. So now our model of the environment M is only a model of the actual environment. It's not perfect, and it has flaws. So when we first did this experiment, it didn't really work. What happened was the agent learned to take advantage of these flaws of the model, and went to parts of the environment that was outside of his training distribution. It learned to cheat. So here we noticed that the agent learned to move in a special way, such that the fireballs rarely get shots. And when the fireballs, some of them starting to get formed, the agent can move in another way to extinguish them magically. So of course, this policy is never going to transfer well to the actual environments. But what we notice is we can, in the sampling process, we can increase the temperature. And by increasing the temperature, we can make this generated environment more stochastic and more random. And we notice that a more random environment is more difficult for the agents inside this environment. And it's more difficult for an agent to take advantages of flaws of the environment. Sometimes the agent may just die with no explanation. Tough luck. But in this more random environment, the agent learns a policy that's able to that's more realistic and is able to transfer well back into the actual environments. So in the results, we can see that by increasing the temperature from deterministic to a high temperature, in the virtual score, the second column is the score the agent achieves in the generated environment. By increasing the temperature, the environment becomes more difficult because the score decreases. But the policies learned transfers better when we deploy them in the actual environment. Furthermore, we noticed that when the temperature is too high, it also affects the quality of the policy being learned. For instance, at a temperature of 1.3, the agent learns perhaps a more risk-averse policy with a lower variance of returns at the expense of a lower mean reward. So the method outlined so far has many obvious limitations. It assumes that an initial random policy is enough to collect a data set that maps out most of the space of the environment, which is not true in any environment that requires any meaningful exploration. So even in a simple swing up pendulum environment from pixels like this one, where the initial policy, the initial random policy mainly gathers data when the pole is facing downwards, we notice that the generative model has difficulty predicting what happens when the controller swings the pole upwards because it simply does not have that much data. Although in this case, at the beginning, the controller still learns a policy to try to swing up the pole. It just doesn't know what to do afterwards. So what we can do is incorporate a simple iterative training loop where we deploy these policies back into the actual environment to collect more meaningful data and retrain the world model on this additional data to build a better model to then train the controller. So after 20 iterations, this world model can learn a better generated environments that maps out the states when the pendulum is swung upwards. And when we train a controller on this improved world model, it learns to more correctly how to balance a pole and swing it upwards. So if you're interested in this line of work, there has been some really recent work, maybe out this month, that explores more in depth the concept of this iteratively training a generative model of high quality model of these environments. And they show that by training an agents inside of these generated environments, we can get really good sample efficiencies on domains like Atari or like a continuous control task from pixels. So in the third work, led by my colleague Danny Jar-Hafner, which I'm part of, we actually try to explore more sophisticated forms of these stochastic dynamic models. So unlike this current work, where for simplicity, we train the VAE and the RNN separately, here we try to train the dynamics model end-to-end on the data collected, and we model everything. And also unlike this current work, where we use a very simple linear controller for simplicity, in this newer work, we also explore things like incorporating a planning module into the controller. And we show that for this control suite task where we learn continuous control tasks from pixels, that we can achieve a pretty good sample efficiency by learning purely from pixels. So this work, in addition to being a paper, it's also available as an interactive web article online at this URL. So if you're interested, you can go on this website to read more about this work and also play around with these interactive web demos. Also, there's code linked if you want to look at reproducing all of the experiments. So this concludes my talk. Thank you for your attention.
How much time do we have? I think we take 3 minutes. So we've got about 3 minutes for questions. So if you have a question, come up to the microphones. I see there's one right there. Go for it.
Okay, thank you for the nice work. My question is, do you have any idea or opinion about training the model with the intrinsic reward? What will be the challenge in that direction and things like that?
So that's a very good question. The idea of an intrinsic reward or curiosity is a natural extension of this. And in fact, Jürgen Schmidhuber has published some work in 1990 where he looks at using the world model to get agents to look at states that is not that aware of. There also are some limitations of these approaches, but feel free to come by our poster later